Thanks everybody for joining us today. I hope that you're all ready to learn a little bit more about the chloride problems in the world and the Chlora analyzer. I know to some of you this is a very important topic, and I know some of you are here to learn, and so I'll try to do what I can to walk you through this. So basically, what we're going to talk about today is how XOS can help you to measure chlorine. We do have Sub-ppm as the header and the title for the presentation, but we'll talk about a variety of things as well. It's just that, you know, with XOS in our instrumentation, our precision, our limited detection is one of our strong suits, and so we will try to touch on that as well. So most of you are already aware of this, but one of the major issues in the refining industry today is corrosion. And I know this doesn't apply to all of you, but for those of you who it does at the refinery and at the test lab helping the refinery, the precise determination of chlorine or chlorides, organic and inorganic, is very important in the industry, obviously. And any chlorides that get into the system and get through the desalter and past other points in the process and down to the finished products, you know, at any place during the process, they can really rear their heads and become an issue as far as corrosion goes. As you know, at the refinery with distillation, with high pressure, high temperature type of things going on, when you have stuff like hydrochloric acid, things can get hairy really quick. So, you know, we've done a lot of work with industry over the last 5 or 7 years on this particular problem, and basically where we're at now is we're just trying to get better and better at it. So one of the main factors for this, and again, you know, I apologize if some of you already are well aware of this stuff, but it's the changing crude sources in the world. You know, you have your opportunity crudes out there that are costing 5 to 30% less. And they provide a refiner with the ability to increase their margins, right? And so what XOS would like to be able to help you to do is help you to understand those crudes better. Some of these crudes are coming from underneath the sea, they're coming from the shale plays, they're coming from upgrading from tar sands. I mean, the chloride content can vary wildly when it's sold on the open market. Chloride content is known in some cases, but it's not always. And it's not always an accurate representation. So by the time it gets down to the refiner, understanding what they're putting into their system is critical. And if they can better understand it before they even put it in and get ready for that, then, you know, it can help to save them money, and it can help save money, it can help with safety, and it can help with any maintenance issues that may occur further downstream. And just some basic numbers, you know, there is an expected increase in crude mix by 2017. And that'll result in a savings for the average refinery. So it does behoove refiners to move this way as long as they're set up to run these crudes well. Down at the bottom here, this isn't necessarily relevant about the catalyst poisoning, but you do see that corrosion events resulting from the undertreatment of chloride and crudes can cost millions of lost revenue annually. The number varies. I don't know specifically how much it is. Everybody says millions. Some people say hundreds of millions. It's a lot of money. And while XOS is just a small piece of that problem solving, we'd like to think that we do add value in that arena. So I'd like to begin talking a little bit about the technology behind the XOS analyzers. And to some of you XRF experts, you can put us on mute now and just do something else. But for those of you who don't really understand XRF and how it works, basically what we're doing is we're taking an X-ray tube and a sample and a detector, and we're using the fluorescence that comes off that sample from the X-rays hitting it to give us a concentration based on a calibration curve. And so over the years, I mean, XRF isn't a new thing for sure. It's been around for a long time. You know, originally it was probably more prevalent in a research lab, and then it became an option for refinery labs and test labs. And then at some point, you know, over the last 10 or 20 years, 25 years, XRF became something more commonplace even at the terminal lab, where you have a less trained operator. So the benefits of XRF, no combustion. Obviously, this is a big thing as far as being a non-destructive process and not requiring to have a large furnace or anything to combust your sample. at a very high temperature. No wet chemistry involved. Again, you're just really putting a sample in a cup and measuring it. Very straightforward technique. Low maintenance. Now, this doesn't apply to every XRF analyzer, but in the area where we play, we are very low maintenance. And if you guys have used our analyzers before, which some of you have, because I know who you are, you will understand that running a Cindy or a Clora analyzer is easier than working your cell phone. You plug it into the wall, you turn it on, you hit some buttons to get to the measurement screen, and then you run your sample, and 5 minutes later you get a result. And then cutting-edge optic technology. Again, this doesn't apply to all XRF, but in our case, this is a very important factor. Our company name is X-Ray Optical Systems, which we've shortened down to XOS. Our bread and butter has always been X-ray optics, and so the optics that we add into this technology platform of XRF are what really separate us from everybody else and give us a leg up, you would say, against the competition. And then finally, it's fast, precise. I mean, again, for those of you who have worked with the analyzers, it's not rocket science. And at the same time, while it's a simple analyzer to use, it still delivers a performance and precision of something that may be a larger XRF research-grade instrument that you would use in a research lab, rather than something out in the refinery where you're getting down and dirty. So, and again, little to no sample prep. I just want to point out a few things here. So I'm going to switch over and turn on my my pointer here. So if you'll see here with traditional XRF, you basically just have your X-ray tube, you have your sample, and you have these X-rays going pretty much everywhere. These are what you would call polychromatic X-rays. They're not really being filtered. They're just kind of hitting the sample. And then where they're hitting the sample, what's coming off of it is X-ray fluorescence. So what's happening there is, if you remember your atom model, when you had electrons and the little valences around the atom, these electrons start to move, and they shift from one valence, one ring to another ring. And when they do that, there's an energy that gets released. And so when that energy is released to move them from ring to ring, there's a detector on the back end that's helped picking up that energy. And you can see here in this diagram that there's a number of different colors. So what we're trying to show you here is that on the incoming, it's not a focused X-ray. It's multi-energy. It's kind of scattered and hitting the sample. And on the back end, the fluorescence that's coming off is not focused either. It's just kind of all coming into the detector at once. So if you were to use this setup for a basic XRF instrument, say, you would be able to accomplish some level of measurement, and you would get some numbers, but when you're talking about sub-ppm or even below 50 ppm for light elements like chlorine and sulfur, it's just not readily achievable without some technological advance. Let's look at the next one here. And so, like I was saying, so that's your typical energy dispersive setup, like we looked at on the previous slide. X-ray tube into the sample and back into the detector. You can see here on this little graph on the left that below this peak there's a large amount of background, and so that's what you're seeing when it's coming off the X-ray tube. You're getting an energy peak, but you're also getting all this background. You're getting some scatter in there, so you're not really focusing it very well. And then over here, you'll see that when you do get to the detector, you do get peaks for sulfur and chlorine, say, but you're still dealing with this large amount of background underneath where I'm running the pointer here. So you still have to accommodate for this big mass of background. And so the peaks you're going to see are much higher. So, with just this type of a setup, you're going to see things like, 50 to 100 ppm well, but if you wanted to see 5 or 10, you would be hard pressed to do it there with a traditional EDXRF setup. Now, there have been advances in the past years as far as using optics for a traditional setup, and what you would do there is use an optic at the front end to focus that X-ray into a monochromatic type beam, which we'll get into a little later, but they are using that on our current analyzer called the Maxine, and I know other of our competitors are doing a similar thing where they're trying to reduce the background on the front end and make it a clean peak of energy, so when it hits the sample, it's a much better clean monochromatic beam source that gives them a much better resolution on the back end. And the next type of XRF I'd like to speak about is what we would call wavelength dispersive XRF. This is more traditional wavelength dispersive technique. So the Cindy or the Clora platform would fall under wavelength dispersive, but we do add further advances, so we aren't technically the exact same. So what you can see here is you have an X-ray tube. Out of that X-ray tube, you have a polychromatic beam like we talked about, and that polychromatic beam is hitting the sample. But on the back end here, you can see where with large WDXRF, traditional WDXRF, they're using things like filters, crystals. They're using pieces on the back end to kind of isolate certain wavelengths of energy and just separate out what they would like to see. But the problem here is that you're still using a scattered beam on the front end, and you're actually using a very high-powered source here too. So that X-ray tube can be up in the kilowatt region, you know, anywhere from 1 to 4. I think even some of them maybe as high as 10. But they're very high-powered X-ray tubes. And what's happening there is they're trying to get as many counts as possible out of this system. So by the time they go through these filters, they still get good peaks. You can see here, they do get good peaks. They get a little less background, but what they're doing is using a higher powered tube to push this peak above the background. And then on the back end, they're trying to get a clean peak by using these crystals, these filters. And in some cases, there can be multiple crystals. They can move, you know, just things that add more complexity to the instrument. And quite honestly, they give you a good variety of elements and good detection limits, but they're not always particularly great at one particular element, which is, you know, where XOS tries to fit in with its monochromatic wavelength dispersive XRF. So we call this cutting through the noise. It's kind of been our tagline lately for our marketing stuff. What we're really trying to emphasize with our monochromatic wavelength dispersive technology is that we're using our optics to not only focus the beam on the front end, but also to focus the fluorescence coming off on the back end. So if you've worked with a Clora or a Cindy already for sulfur or chlorine testing, you realize that you're getting a very clean number at the end. Because on the front end here, we're taking what would be a polychromatic tube, a polychromatic X-ray source, and we're focusing it through a first optic here. And that optic is a doubly curved crystal. And so what that does is it's in there and it's curved at the right angle. So when the X-rays hit it, they're pushed off and they're in a single energy band before they go to the sample. So instead of having all this scatter and all this energy level, it's kind of, you know, just throwing everything out there. It's very focused. It monochromates. And so when it hits the sample, you can see here on this graph, very clean peak of energy, very, very clean, hitting the sample, just trying to stimulate that fluorescence for certain lighter elements. And then when the fluorescence is coming off the back end, it's hitting this second optic, which would be used for what we would basically amount to filtering. And so what's happening is it's taking the fluorescence that's coming off here, hitting this optic, which is curved to a specific angle. So on the back end, all you're getting is chlorine K alpha energy or sulfur K alpha energy. And by that, again, I'm talking about the electrons moving from valence to valence on the atom. So by the time it gets to this detector, which in a typical Clora analyzer is a very simple detector, it's just a pulse counting detector. There's nothing left but these chlorine, these chlorine X-ray energy. So this one's it says sulfur. I apologize for that. That's on my end. But so imagine this is your chlorine peak. Very clean. You can see here there's very little to no background underneath these peaks, and that's coming off here. And then by the time you get through the second optic and you're coming into the detector, you're getting nothing but that peak. And so again, you know, this technology, this MWDXRF technology, is something that XOS has patents around. You know, it's something that we've really perfected over the years. And for measuring light element at low concentrations, it's key for getting these sub-ppm levels. And so what we've done is we've made a suite of analyzers that are based around these, right? And so we've already talked about the Clora, and that's what we're going to talk about here. The Clora is based on that monochromatic wavelength dispersive technology, and some of you already have them, I know, on the call. Some of you have worked with them. You can see here in benchtop format, it's not a large instrument. It sits right on a laptop very easily. It's only a little bigger than, say, an old tube TV. And then you have your online instrument, which we'll get into later as well, but we've managed to port the technology into a process format as well. And so what the Clora gives you here is it gives you the opportunity to run all these different sample types on it very easily, from crude to process streams like naphthas and heavy oils, finished products like gasoline and naphtha cuts and anything else, aqueous samples, overhead waters, sour waters, and then even things like aromatics, benzene, toluene, xylene, and powders such as catalyst. We have been able to measure catalyst on the Clora to determine, what the chloride content is, to figure out, if it's too much, too little, how is that affecting your processes. The current Clora, as it stands, does have a method behind it, and that's D7536, which is a method specifically for aromatics, like we talked about, for toluene, benzene, xylene, samples like that. And the method is written around concentrations from 0.5 ppm up to 15 ppm. So currently that is the only ASTM method we have, but we are working on other things, and further into the presentation, I will touch on those a little bit. The limited detection for crude is about 0.2 ppm at 300 seconds. For other products, it's probably closer to 0.1 to 0.15, depending on the product type it is, and even depending on the sulfur content, because there is some level of interference from high percent levels of sulfur. You can see here that the repeatability at 10 ppm is about 0.8 ppm, and the reproducibility is 1.4 ppm at 10 ppm. So very, very good numbers, great numbers for the applications that we've been in over the years, such as the crudes and the process streams. But there has been an emphasis on doing better on that and getting lower and lower, and I'll touch on how we've improved on that here shortly. So like we discussed on the previous slide, there are a number of applications that we are involved in. This isn't all of them, but just to name a few particular ones, measuring distillates such as gasoline and naphtha, potential contamination from organic chlorides. So as we talked about earlier in the process, there is a level of chlorides that seem to be getting downstream, past the desalter, through the processes, and into different cuts through the distillation process. And then the feedback we've been getting from industry is that most of these end up residing in that naphtha cut, or possibly even the gasoline stream, even further down there. When that naphtha fraction is desulfurized at the reformer, that hydrochloric acid, which we talked about earlier, can crop up, and it can cause extreme and rapid corrosion. Like we said, high pressure, high temperature situations, you could run into issues there. Aromatics testing, like I said previously, the benzene, toluene, xylenes of the world, these actually command a very low level sub-ppm performance. Our method is written from 0.5 ppm up to 15 ppm. The QC levels are usually less than 1 ppm for most of these products. And with the Clora, it's a very simple process. These are clean products. You put them in a sample cup and you just run them. It doesn't get much easier than that. And then finally, with desalted crude oil, like we talked about at the beginning of the presentation, at and around the desalter, you want to know what your chloride levels are. You want to know coming into it what your expectations are. How much salt are you removing, and then once it gets through the desalter, you want to be able to understand what's left over. And out of what's left over, Is it organic? Is it inorganic? You may not know right away, but you'll know immediately. You know, if you have a core instrument that you can get a 5-minute measurement and get that number. And so if you're running typically at 2 ppm after the desalter and that spikes up to 5 or 6, you know there may be a problem. You know, your desalter may not be running right. You may have seen a spike in organic chlorides that you don't know about. So it gives you a quick way to screen for that and get to the root cause so you can help your process. And so you can see here I've listed a few important parts of that, but I've also brought up that the Chlora 2XP. And so the Chlora 2XP is really the crux of what we're talking about here today with our improvements for measuring for sub-ppm measurements for chloride and chlorine and fuels and raw streams and things like that. It gives you the ability to recognize these smaller changes quicker, not just after the desalter, but also further down in the process, things that can stem from poor efficiency of the desalter or even just from contamination, as I said before. And this Chlora 2XP is an improvement over our current Chlora. So you can see here, this is basically mostly the same stuff, but you can see the improvement for the numbers as far as the limited detection goes, and then your repeatability and your reproducibility. Here we have the numbers listed at 0.5 ppm. What we're really trying to stress here is that with the improved LOD of 0.07 ppm at 300 seconds, we can achieve a much tighter statistical precision at low levels, even at 0.5 ppm, and it's gonna help you out across the board, not just at 0.5, but even if you're measuring at 5, the numbers are going to be tighter. If you're measuring at 3 ppm, the numbers are going to be tighter, and it really gives you an advantage when you are already looking around 1 ppm and you want to have more clarity, or you were trying to measure at say 1/4 ppm on the old Chlora and you just couldn't quite get there consistently, and so we got feedback from the field. You guys talked, we listened, we made improvements, and I'm going to talk about what we've done here a little bit. So the major enhancements to the Chlora 2XP revolve around the optics. And so at this point, we're on our 4th generation of doubly curved crystal optics. My legal department says I can't say too much about them, but basically what happens is that the more counts you get, the better your statistics are going to be, and the lower your limited detection is going to be. And so what we've done is we've improved the optics. We've kind of beefed them up a little bit. We've changed the configuration and given the system more counts. And by giving it more counts, we've dropped that limited detection down and increased the precision. And that's very well suited for low-level measurements due to that enhanced sensitivity. And there was no need for us to change the X-ray tube in it. Really, using these new optics, we use the same tube and we're getting better performance out of it. So you don't have to worry about us putting a higher powered tube in it that'll cost more money for you to replace down the road, that'll run hotter, and any of these factors. We're using our core technology to improve the instrument without passing anything on to the customer as far as more maintenance or higher maintenance costs. The second thing we did is to put a silicon drift detector inside of the analyzer. These are pretty standard across the XRF industry these days. You'll see on many spec sheets for multi-element analyzers, single-element analyzers, research-grade equipment, that people are switching over to these higher-powered, lower background detectors. They're much more efficient, and they give you a much cleaner signal. So if you remember in the previous slides where I talked about on the back end for the regular Chlora, we were just using a standard pulse counting kind of detector. What we've had to do here to get that lower limit of detection is improve this detector to basically what's current technology. I wouldn't call this a leap in technology by any means, but it is an improvement over the older Chlora for something that people are already using in other XRF instrumentation. And then the final enhancement we've added, is the automatic sulfur correction. So again, we got some feedback from the field that, with XRF, there is a level of correction needed for samples with high sulfur content. Now I know, for things like aromatics, this isn't going to come into play, but for those of you running crude oils, being able to automatically account for that sulfur level is a great add-on, and I know there's there's already people doing it, so we're getting to the party now, but we think we found a great way to do it, and we think it'll really benefit you long term. And it'll allow you to get better precision too. What you're doing is you're taking out another variable, right? So instead of running your sulfur test on another analyzer and then taking the error from that analyzer over to the Clora and plugging that number in, you're getting a clean number from the analyzer for counts, and using those counts, the system is able to automatically correct for that. And so you can see there, you know, we're using that new detector, we're using another channel on that to pulse for sulfur. We made some improvements to the optics so we can get a little bit higher of a sulfur reading simultaneously, and we added that algorithm to remove the high sulfur interference. And it really just comes down to a button on the screen to turn that on and off. So, I mean, really, a lot of people would probably just choose to leave it on all the time. So, but if you've used a Cindy or a Clora before, you know that our interface is very simple. It really is all about just tapping buttons and getting what you want. So with this sulfur correction, that's really all that you need to do. When we were making the 2XP, and I know for some of you, it may seem like I'm being kind of teacher-like here, but when we were making the 2XP, we found that when we talked to customers that wanted to achieve low-level measurements that weren't quite getting there, that one of the problems was SOP, you know, was having best practices, was having better ways to do what they've been doing forever. And so when we went to do this project, we looked heavily into this. And looking heavily into it, we learned that if we put it down, people may not listen to all of it, but at least if we can put something in writing in front of the customer, then you guys can take this and run with it and make it your own. But in order to achieve good numbers at, you know, say 1/3 of a ppm, it's critical to clean. I mean, you guys know your labs. These aren't always the cleanest labs in the world. You got things flying around. You got people coming in and out. And so maintaining some practices are critical. So what we would ask you guys to do is to, you know, clean the sample chamber. So on the XOS analyzer, the sample chamber is really just at the top. You can see here what we call the primary window. So there's really a small area where the sampling is actually done. So improving your maintenance of that area between cleaning it with IPA, between using can duster to clean it up, and just making sure that you're consistent with it, it really can go a long way. And then the other thing we've done is we've improved the secondary window. So previously the design for our secondary window was up underneath the sample basket. And you can see here that we've actually applied that primary window that secondary window directly over our primary window now. So I think that really does two things. First, it keeps any contamination from falling down into that sample basket where it would have fallen down before and been very difficult to clean. And second, I think it just gives you an easier way to clean it in general, if there was any spillage or anything underneath it. So it is an improvement. We did see our consistency go up when we made these improvements and started following these cleaning procedures. You can see, and I can send this to any of you, so if anybody has a request for this, I'd be more than happy to send it over. But at the end of the day, it is critical to make sure that you maintain your cleanliness. And then also some other things that we've added onto here is just preparing the sample. Make sure that you're consistent with when you make your samples, that you're cleaning the area around you. You're making sure that you're not using cups that have been sitting out for a week in the open air. Making sure that you're putting your film on your cups right. I mean, I know this all sounds very remedial, I'm sure, but even, you know, our statisticians who have done studies for us at ASTM before have said that the biggest variable between labs is the users, and part of that is the sample prep. So we do have this document now to help walk you through this. It was originally made just for the 2XP, but I know I've been working with some of the folks here to roll it out for the other product lines for making samples. Pretty simple. In the Chlora 2XP case, we have been at times running 2 samples for 300 seconds and averaging the runs if you're not getting consistent data. But for the most part, you know, we ended up running a lot of the stuff just for 1 measurement at 300 seconds. So. let's see here. So a few more advantages of the Clora. And so this data is going to be a little more specific to the 2XP. And this really comes right off the brochure. You can see here our improved little r and big R. And while it may not look like as much on paper as you're probably thinking, you know, if you compared one against the other, you really do see a difference. You know, I've had major refiners, you know, comment, you know, when they're running the Clora 2XP next to the regular Clora, that when they're running down at these low levels, that they are seeing a drastic improvement. And that improvement, a lot of it comes from the counts that you're getting with these new optics. And even at levels like 5 ppm, you're going to get tighter data. So, you know, if tight data and precision is you know, one of the critical things on your list when it comes to chloride testing, you know, we're here for you. And then again, with the water, with water samples, we've also been able to improve things, because if you're not aware, with aqueous solutions with a high oxygen content, anytime there is a drop in sensitivity when running water samples on the Clora. It's still very easy to run, but you would have to have a different calibration curve or use a correction factor. You'll still have to do that, but with the improved amount of counts, we're actually improving the precision for the water measurement and lowering that LOD as well. So if you're looking at aqueous samples, you know, you're looking at a limited detection now of, say, half a ppm. And just some results here I wanted to share with everyone. It'll be included in the presentation when we send it out to everybody, so we don't need to go over each and every little number on here. But we did some testing on gasoline, pulled right from the pump, you know, running 600-second runs on it. You can see it was running pretty tight, around 1/3 of a ppm, and a RSD of about 9.9%. I mean, very good numbers, and you know, lots of people like to put up numbers about what they run their standards. You know, they have a standard and they ran their standard and they got this, but we actually wanted to go out, take some real world data, and we did that here, tight data around 1/3 of a ppm, and then over here at 1/2 a ppm, you know, fairly tight data here as well. I don't know, this is a naphtha sample, I believe. One more set of measurements here, just to show that we're not all about the finished product. We did some work with some heavy oils, some heavy gas oils that were down around the 1 ppm kind of region. Again, just a nice set of data to look at. You know, I know it's not all that exciting, but 20 runs here, you know, you got an RSD at 2.78, you know, standard deviation of 0.03 on a 1.4 roughly sample, real world sample, just put it in and measure it. Next, I do just want to talk a little bit about what we can do for you on the process side of things. We do have a Clora online instrument, which we have had for three years now, I believe it's been. It's based on the same platform as the regular Clora. You know, you're getting an LOD of about 0.2 ppm, 0.5 ppm in aqueous solution. And what we're doing here is a continuous measurement. So if you wanted to put this thing out in your process somewhere, you can install it around the desalters, around you know, around where your naphtha feed is, any of these places, and get good consistent chloride measurements at low levels. And then it gives you the benefit of not having to walk it into the lab every time. So if you did have a case, and I'll just skip to the next one quick, but I may go back to the next slide. I reserve the right. But so to set up a Clora online, you know, one of the things we're thinking is to set it up around your desalter, right? And you can see here in this diagram that optimally, you know, it'd be nice to know what's happening post desalter as well as what's happening, you know, before it comes in, what the raw is. And so maybe being able to give you some type of balance there to figure out what your desalting efficiency is, you know, what you need to be doing to treat, you know, your crude oil as it's coming through the desalter. I know, you know, we've been speaking to a number of chemical treatment companies over the years, and you know, what we've heard from the industry is that there's a want to know this type of stuff, and there's a want to know these kinds of details in real time, and you know, we'd like to think that we can provide a solution for that. And like I said, so with our online instrument, what we're doing is we're continuously flowing the sample through what we would call a dynamic window module. You can see this here bolted onto the side of the analyzer. And what's happening here is the sample's flowing up through. There's a sample film in here. It's that little yellow slit in there. That's a piece of Kapton film. The sample's constantly moving by. It's getting hit with X-rays, just like the earlier slide of MWDXRF I showed you. X-rays coming out of the source, into the first optic, hitting the sample, coming off the sample into the second optic, and down into a detector. So same basic principle, just gives you a continuous measurement, which I think is a very nice feature. Just some quick data here, you know, at about 3 ppm, very tight data between 3 and 3.5, I'd say. It doesn't really creep up much more than that. And this is desalted crude oil. Another desalted crude here, around 5 ppm or so. The trend, you know, what you're seeing here on the red line with the red data is the actual 5-minute measurement, and the blue is a 15-second trend measurement. So you can actually detect major upsets much quicker than a 5-minute measurement. You could detect them within 15 to 30 seconds if you were paying attention to what that trend was doing. So. I did want to talk briefly as well about the AccuFlow technology. You know, it's a concept that we came up with from our online instrumentation that in the lab, you know, there are opportunities for some of these samples to settle out. Heavy crude oils, you know, that have a high salt content, you know, with those salts, as the measurement runs over time, they'll start to fall out of the solution and down towards where the X-rays are actually hitting it, giving you kind of an erroneously high measurement. And what we've done is create this AccuFlow technology, and I'd like you all to watch just a brief video on that. And if you give me a second here, I'll pull that up.
XOS, a longtime provider of breakthrough. Combined with XRF, new AccuFlow technology allows for measurement of continuously flowing samples, the next generation in benchtop analysis. XOS analyzers are easy to use, and XOS can supply you with all the materials you'll need for either static or continuous analysis. Here we see a static measurement using the Clora. To start, simply open the lid. Place your sample cup inside. Close the lid. Select the static measurement. Load your sample. Hit the measurement button. The measuring screen provides you with a status bar as the analysis progresses. In a matter of minutes, your results are in. Like all XOS benchtop analyzers, the Clora also allows you to measure from sub-ppm level up to % weight levels. By applying AccuFlow technology to an XOS benchtop, as seen here on the Clora analyzer, we can eliminate the settling of particulates in the sample, resulting in an increased level of accuracy that surpasses traditional benchtop analysis. In this animation, we see how particulates settle over time during a static measurement. Here we see how AccuFlow eliminates particulate settling effects by giving you direct measurement of crude streams as they exist in the refinery. To prepare to use AccuFlow technology, simply assemble the AccuFlow kit provided for your XOS benchtop analyzer. After you assemble the syringe, draw back the syringe's plunger and take in your crude oil sample into the syringe. After opening the lid to the analyzer, place the filled syringe inside and lock in place. Close the lid, then select the button for measurement. Similar to the static measurement process, a summary screen provides you with a status bar to track the progress of the analysis. In a matter of minutes, the result is in. The Clora is just one of a full line of benchtop analyzers that can be equipped with AccuFlow technology to eliminate the settling of particulate. At XOS, we believe that better analysis counts. Innovative X-ray fluorescence technology powers the detection and precision capability of XOS analyzers. and the ease of use and reliability of XOS analyzers enable their operation in tough environments, from mobile vans to refineries, plants, and pipeline terminals. To find out more about AccuFlow technology and XOS's full line of analyzers, visit our website or contact an XOS field expert today.
Okay, I'm just going to go back to sharing the presentation here. I apologize if you guys didn't have any sound there for a little while. I turned it off to clear my throat, and I didn't realize that it was the main feed. So, and I hope you enjoyed getting to see the back of my head. So basically, as you can see there, the AccuFlow technology, what we're doing is trying to remove a problem that plagues typical XRF instrumentation, which is settling. We've seen this with chlorides, seen it with some things like iron, and even phosphorus is kind of a little more volatile in solution as well. You know, you see some settling out over time. And we do have, you know, data that basically shows this. I'll just skip through that since we already saw that. But so you can see here, this is your typical chloride measurement. This is us leaving it in there over the span of an hour, which is a little bit overkill. But, you know, we're really just trying to prove a point, right, that you start down here below 100 ppm, and you're creeping all the way up to 1600 ppm over an hour. After a 5-minute run, you can see here you're already approaching 400 ppm, which obviously is not an accurate number. And so feedback from the field dictated to us that we needed to find a way to help our customers who this was important to. And that's where the AccuFlow technology was born out of. And you can see, again here, statically measured the creep over time, over a 3-minute measurement run. And then here, when we put the flow through, the AccuFlow on, just a nice tight set of data. So if your thing is measuring, you know, raw crudes and even some desalted crudes to a certain extent, you know, and they have a high chloride content, and you see these kinds of effects, you know, the AccuFlow might be the right solution for you. I guess that's where I'm going with this. A little more data here. You can see both things on the same chart. Your blue line is your static measurement, and you can see it creeping up over time. And then your purple, green, and yellow, that's creative colors. Those lines are those are all pretty stable. As you can see, the AccuFlow feature has been turned on, and they're using that syringe drive to flow through. So a couple more. Finally, I just wanted to wrap up, you know, with our efforts at ASTM. I know this is important to some of you folks out there as far as, you know, what is XOS doing to give us a piece of technology, but also to give us a piece of technology that has, you know, a method written around it, something we can point back to, you know, as far as being able to test properly, you know, do the same thing twice, and to have a precision statement. And one of the things we're doing right now is working on this D4929 method to add a method C, which would be XRF technology. And so this is a typical method for measuring organic chlorine and crude. And you can see currently there's a few different ways you can do this written in the method: sodium biphenyl reduction, combustion, and MC. What we're looking to do is maybe make it a little simpler for people and just tack on running the final piece on an XRF analyzer, which I know some of the industry is already doing to a certain extent. They're running a version of our aromatics method, which has been modified, but we would like to make it a little more official. And so since the precisions are given separately for each of these different methods, it should be relatively easy to add a method C to this. And I know our ASTM here, headed up by Leslie, are working very hard on this. So, you know, we presented some results back in June at ASTM, and we're preparing a pilot study. We did an initial pilot study, and now we're preparing for the larger study. And I can show you the pilot study data here. You know, we have this Saharan neat crude where, you know, this is in ppm, obviously, milligrams per kilogram. This was with the standard Clora too, so you can imagine that the data set with the 2XP would only be tighter. But you can see this data set here. It's very nice repeatability statement and a reproducibility statement based on this small data set. It was enough for ASTM to kind of give us the go-ahead to move forward with a full-on task group and a work item and a study and all that. So currently working through that. Hope to have some more information for you guys at at ASTM in December for those of you who go. And we're also working on some other things with raw crude oil, just as far as getting the total chlorine number in crude oil. And I know our ASTM team is looking into that as well. So we're at the end here, and this is our shameless plug for demonstrations. So if anybody would like to get in contact with me or anybody else here at XOS, we'd be more than happy to set you up with seeing a Clora, seeing a Clora 2XP if you would like, even to just coming out and talking about your options with you. We're always happy to do that, and it's something that we know we need your feedback to carry on, so we would appreciate that. And at this point, I do have one more slide, which I forgot about. But this is our whole lineup of analyzers. This is all of our analyzers for the petroleum industry. You can see your Cindy's there. Those of you who already have one are aware of them. But for sulfur measurements in gasoline, diesel fuel, anything up to crude oil, very simple to use, just like the Clora. We have a signal analyzer for measuring silicon. And then we have a Phoebe analyzer for phosphorus, the Clora, as we talked about, for measuring chlorine, and then the Maxine, which is our multi-element analyzer. And we did a talk on that last year, so if you guys would like to have access to that talk as well, we'd be happy to send that over if you have a request afterwards. At this time, I'd be happy to take any questions, and would just like to point out again that we'll try to get to as many questions as we can, and any that we don't, we'll follow up with at the offline, and then get to you guys the feedback you need. And anyone who registered will get a copy of the presentation emailed to you, I believe, because I'm sure that'll be a number of questions will be, can I get the presentation? So, so any questions, please feel free to go ahead and type them in, and all right, so just looking at a few of the questions here. One of them is it possible to add a second element to the Clora for measurements such as sulfur? That's kind of a long-term question. It is something that we're looking into. Obviously, now that we can do sulfur correction on the Clora, we can get somewhat of an idea of the sulfur content in the sample, but we're not quite to the point where we can be reporting out both elements at the same time. It is something that's in the roadmap for the future, though, so stay tuned with that, and we'll try to get there. Obviously, we would like any of your feedback on which elements would be beneficial besides sulfur, if you had an analyzer that did chlorine and phosphorus, say, or anything like that. And just any elements you guys are generally interested in, we're always happy to hear about. All right, let's see what we got. What else do we have here? Are there any interferences? Well, like I talked about earlier, there are interferences related to high amounts of sulfur, which with the 2XP we've tried to do away with automatic sulfur correction. And then there is an interference from high levels of oxygen, as I stated when we talked about the aqueous samples. And that can be gotten around either by calibrating for it or just applying a correction factor, and we would be happy to supply tables or anything that you may need if you need a correction factor for any particular samples you're running. I do have a question about the Maxine. I know we didn't talk about that here, but I'd be happy to briefly touch on what it does, and maybe we'll send you the presentation we did last year. But the Maxine is multi-element. It does about 30 elements of interest to the industry. Typically, are low-level nickel, vanadium, iron, calcium, zinc. It can do sulfur and chlorine, but not to the levels that a Clora or a Cindy can do. It just suffers with the light element performance. So it's a nice analyzer for crude oil testing and lubricants testing, when it comes to a multi-element analyzer. But for low-level precision, you're still looking, for chlorine, you're still looking at a Clora analyzer. Is there an effort to use the Clora to look at organic chloride or non-extractable chloride directly in crude oil outside of efforts with D4929? Right now, it's really just a lot of internal stuff. It's not something where we're actively working on that, but we do have we do have some applications chemists here, and we'd be happy to talk about that with you offline. Is there an auto sampler available? Yes, there is an auto sampler available for the standard Chlora, but at this time there isn't one available for the Chlora 2XP. In the future, we might be looking into that as well. So if you guys have any feedback on that, you know, we'd be happy to talk about it. What else do we have here? Is it possible to measure solids on the Chlora? Measuring solids is possible. It would depend on the uniformity of the sample, the homogeneity. If you can get it into a sample cup and you know it's a uniform sample, then, you know, if we know the makeup of it, there may be a calibration needed specifically for it, but depending on what it is, we might be able to get away with running solids on it without a major issue. So. All right. Well, that looks like about all we got. So, again, thank you everybody for participating. I would like to say that you know, these things are always good for me because I always learn a lot from you guys afterwards when I get your phone calls and emails. And thank you to Mary for helping me put this on here at XOS, and to Leah at WebEx. Have a good day, and we'll get back in touch with all of you who've asked questions who I haven't answered here. Thank you.